We have been discussing Monte Carlo simulation methods for studying randomly excited structural systems. So, we reviewed certain principles of statistics in the previous lectures, and today what we will do is we will discuss how to simulate random variables on a computer. So, let x be a random variable with probability distribution function Px of x. The problem on hand is how to generate samples xi say 1 to n of x on a computer, so that these numbers are statistically indistinguishable from realizations of the random variable x. So, that is the problem. This we have to do on a computer, not through a physical device. The starting point for this discussion are what are known as pseudo-random generators. These are deterministic algorithms which produce outputs which are statistically indistinguishable from realizations of random variables. These random variables are typically taken to be uniformly distributed between 0 and 1. So, pseudo-random number refers to random numbers which are uniformly distributed between 0 and 1. So, this is a starting point in digital simulation of random variables. Random numbers are taken to mean numbers which are distributed uniformly in 0 to 1. So, the first task on hand is to how to simulate realizations of uniformly distributed random numbers which are uniformly distributed in 0 to 1. There are certain deterministic algorithms which will produce these random numbers, and these are known as linear congruential generators. So, the algorithm here is xi is a xi minus 1 plus c modulo m. So, I will explain what these terms are. Xi's are generated through this map, and Ri, which are the pseudo random numbers, are defined as xi divided by m. These constants here a, c, m and x naught, it should start with the I equal to 0, which is x naught. X naught has to be specified. They are integers to be specified by the user. So, a is known as a multiplier, which is positive, c is known as increment, which is non-negative, m is the modulus, positive, x naught is a seed greater than or equal to 0. This operation modulo m means modulo m returns the remainder after dividing this number a xi minus c plus c by m. The remainder is returned as the output. Now, this is a map whose period is less than or equal to m. That means, for each of these maps there is a quantity known as period, and after suppose I runs from 1, 2, 3 and up to that period, then it repeats, the same sequence repeats. This period for this algorithm is k, and k can be less than or equal to m. So, ideally we want k to be equal to m to make best use of this generator, and there are theorems in number theory which states under what condition a congruential generator has full period m, and it has something to do with choice of a, c and m. So, the GCD of c and m must be equal to 1, and a equal to 1 mod p for each prime factor p of m, and a 1 mod 4 if 4 divides m. So, if these conditions are satisfied, the period will be m. So, we need not worry about the theoretical background behind this, because it is a specialist area which belongs to the domain of computer science and number theory. So, we will use these tools as a starting point in our discussion. But to understand what we are going to use, it is useful to simulate the output of this map for a few choices of the parameters. So, let us take xi as 9 xi minus 1 plus 3 modulo 2 to the power of 4. So, the period here can be 16, and indeed it turns out that after every 16th number the signal repeats. So, this part of the signal simply repeats after every 16th number. This is the 16th number, and this part repeats So, there are 16 random numbers that we can generate through this, not very useful for practical applications. Now, similarly we make another choice, again the period is 16, where what we are doing is we are changing the initial value. This initial value is 3 here and this is made as 12 here, and this is known as seed of the random number generator. Okay. So, for different seeds we get different sets of 16 numbers, but that repeats. Okay. Now, on a computer typically the choice of AC and M will read something like this. This M is 2 to the power of 31 and this A is this large number, and for a x naught equal to 12 I have simulated 100 numbers and I have shown the plot here, and you can show that the period of this generator is given by this number. So, this is a fairly large number. If your application uses numbers, total number of random numbers that you are using is less than this, you could go for this. So, if you take 100 such numbers and draw the empirical probability distribution function, if it is uniformly distributed, it should lie along this red line, and we can conduct, for example, a hypothesis test like Kolmogorov-Smirnov test and see whether we can accept the hypothesis that these numbers are coming from a population which is uniformly distributed with 0 and 1 at some significance level. So, that is when our hypothesis testing helps us to assess the random numbers. So, if I plot now these 100 numbers, suppose I am plotting Ri plus 1 versus Ri. So, our worry will be, is there any order in this sequence of numbers? If it is truly random, there should be no hidden orders. So, here if I plot I plus 1 versus I, this should be randomly distributed in this space. So, similarly I can do similar exercise in higher dimensional spaces, and we never know whether such an order exists or not. Okay. So, we have to go on checking. So, if I use 10,000 these numbers, you can see that the agreement between uniform target uniform distribution and the empirical distribution is pretty close, and again we can do the KS test and see whether we can accept the hypothesis that these numbers originate from population with uniformly distributed probability distribution. Now, these 10,000 numbers are plotted, that is Ri plus 1 versus Ri is plotted, and we can see that this is some kind of a random image. I cannot discern any pattern here. So, there is no reason to reject them, these numbers as being random. This story is not always so, I will come to that slightly later. Now, I have shown a few random numbers starting with different initial conditions, that is seed. If I start with 10, I get these numbers. If I start with 11, I get different numbers, and so on and so forth. Okay. So, just for illustration how these numbers behave. Now, if I take M to be 256 and A to be 13 and C to be 3 and generate say a few random numbers, and I think I have generated some 10,000 numbers, and if I show the empirical probability distribution function, it matches very well with the target distribution. But if you look at the I plus 1 versus I plot, there is a structure here. So, obviously, this is alarming. We cannot accept these as random numbers. More such examples. I have shown the parameters A, C and M. So, we can see here this is some, in all these 4 cases there are quite a good amount of patterns that emerge, and these cannot be trusted as random numbers. So, if you make these choices, I mean if you tried generating random numbers, then you have a tough task on your hand. You have to perform several tests, and in the literature there are several tests that are discussed in this context. So, danger lurks everywhere. So, you have to be cautious. Now, how about order in higher dimension? I am plotting I plus 1 versus I. Suppose I plot I plus 1, I plus 2 versus I plus 1 versus I in a 3-dimensional space, and they should be randomly distributed. How do I know in 5-dimensional space that there are no orders, right? So, this is a question that is almost impossible to answer. So, it depends on the application. Suppose you are evaluating a 2-dimensional or a 3-dimensional integral using Monte Carlo simulation, you should ensure that at least in 3 dimensions there are no manifest orders in these numbers. So, this is where one has to be cautious. Now, there are other strategies like combinations of generators to deal with to ensure that there exists randomness in higher dimensions. So, there are various algorithms, one of that I have listed here. So, you generate you take 3 generators, xi plus 1 is this, yi plus 1 is this, zi plus 1 is this, and then you define ri plus 1 as a kind of a sum shown here modulo 1, and this will be this is supposed to behave well in 3 dimensions, well in terms of being random. Now, I talked about seed. So, on a computer when you are generating random numbers, if you want to debug your program, every time you run the computer, suppose you are generating 10,000 random numbers, it is useful to get the same 10,000 numbers. One way is to generate them and store and read from the disk, but if in the program it is infeasible, if you are really doing a practical problem, to store all the random numbers before and draw from them. So, the best way is to start with the same seed, and that would ensure that we get same set of random numbers. So, this also this helps us to reproduce the sequence on one hand, and also we can avoid the storage of random sequences on the computer. Now, if you want to prolong the sequence, you have generated 10,000, you need 10 more thousand random numbers, you can use the last number in your first sequence as a seed for the next one, so that you continue with the same sequence. Or you can start a new sequence with a randomly chosen seed, for example, clock time on the CPU or some other numbers, but this approach leads to numbers that are not reproducible. If you do not specify a seed yourself, you cannot reproduce the sequence of random numbers. I am talking about generation of random numbers on computers. There are strategies where the random numbers are drawn from a physical process, for example, noise in drawn from atmosphere through a radio. So, that noise is digitized and used as random numbers. So, there is no algorithm there, and we bank on certain physical mechanisms for production of random numbers. But for the Monte Carlo application that we are discussing, we bank on random numbers which are generated on a computer. So, selecting pseudo-random number generators, you need to I mean this choice is based on theoretical studies on random number generators. It involves number theory and study of nonlinear maps. So, if you are doing empirically, you have to test for uniformity, test for independence of pairs and k tuples and so on and so forth. So, there are some guidelines, period to be at least 2 to the power of 27, that is about 10 to the power of 8, and k tuples about up to the order of 10, as uniformly distributed as possible in k dimensional spaces. So, you can do some of these tests using hypothesis testing methods and see whether these numbers pass the I mean you can accept these numbers according to the given level of significance. Now, the moral is if you are using pseudo-random numbers on a computer, you need expert help. Most of the professional softwares have random number generators, that is numbers that are uniformly distributed in 0 and 1, which are based on algorithms which are theoretically investigated, and you are advised to use such algorithms. If you attempt to simulate your own random numbers, you have to be very careful about many aspects of the nature of these random numbers. So, use what is professionally available and trust, that is a moral. There are few references I have listed here. There is a book by Dagpunar, Ripley, Robert and Casella and Liu, which discusses not only the details of pseudo-random number generators, but also few of the methods that I am going to discuss in due course. Now, we have generated now uniformly distributed random numbers. How do we generate say Gaussian random numbers? So, we here many strategies are possible. We recall when we studied transformation of random variables, there was an algorithm known as transformation known as Box-Molar transformation. We will quickly recall what it is. So, let x and y be independent and uniformly distributed random variables in 0 to 1. I define u as minus 2 ln x to the power of half cos 2 pi y, and similarly v, instead of cos here I have sin. The problem is to find the joint probability distribution function of u and v. We have solved this problem and we have shown that u and v are independent and jointly normal, they have 0 mean and unit standard deviation. So, that we have done. These are the steps where we find the Jacobian and go through this, and we get this joint probability density function. That would mean u and v are independent, u is normal with mean 0 and standard deviation 1, v is normal with mean 0 and standard deviation 1. So, we could use, now that we know how to generate uniformly distributed random numbers, we can use Box-Molar transformation and generate Gaussian random numbers. So, generation of Gaussian random numbers, once you know how to generate uniform random numbers, is reasonably straightforward. Again, if your random number generator in the for uniform distributed random numbers is bad, it will get into u and v also. So, you have to be careful. So, I have used 1000 numbers and plotted the empirical probability distribution function of random Gaussian distributed random numbers. Blue line is the simulation, red is the target, and again we see reasonable agreement between the two. If I use the same results, if I plot on a normal probability paper, they look like this, and qualitatively we can see that these numbers are lying on a straight line. And I did perform the Kolmogorov-Smirnov test at 5% significance level, and I reached the conclusion that we can accept the hypothesis that sample is drawn from a population of normal random variables with 0 mean and unit standard deviation at 5% significance level. So, it passes the test. Similarly, 10,000, the agreement, as we can infer from visual inspection, is much better now. And if you conduct the test, again plot on the do the KS Kolmogorov-Smirnov test, again we will be in a position to accept the hypothesis that these numbers are drawn from standard normal population at 5% significance level. So, these numbers I have displayed in 2-dimensional map u I plus 1 versus u I, and we do not recognize any pattern in this. So, they seem to be acceptable. Again, just a word of caution, I have used the congruential algorithm for generating uniform distributed random numbers. X and y I have simulated following this prescription, and then I have used the Box-Molar transformation, and the results on u and v are shown here. This is ui plus 1 versus ui, this one, and this is vi plus 1 versus vi. So, this has disturbing levels of order in the numbers, and if you use these numbers in your modeling work, you are bound to face lots of difficulties. Now, I talked about Gaussian distributed random variables. How about an x which has a given probability density function Px of x? Now, we can take the as a starting point our ability to generate standard normal random numbers, that means 0 mean unit standard deviation random numbers. Now, we consider the transformation Px of x is phi of z, where capital Phi is the probability distribution function of standard normal random variable, and x is the target random variable, and x is written as x is equal to Px inverse phi of z. So, one of the prerequisites for applying this method is that you should be able to invert the probability distribution of the target random variable. Now, if you follow the rules of transformation of random variables, you can show that if you generate x according to this rule, the probability distribution function or density function of x will be identical to the target probability density function. Now, so what are the steps? We simulate standard normal random variables, use this transformation and get samples of x. So, this is a very straightforward exercise, provided you know how to invert your probability distribution function. So, we can start with an exponential random variable. the probability distribution function is 1 minus exponential minus lambda x. So, the transformation here is 1 minus exponential minus lambda x, this is random variable x equal to phi of z, and from this if I solve for x, x will be minus 1 by lambda log of 1 minus phi of z. So, I simulate normal random variables 0 1 and use that transformation generate the corresponding sample of x. So, I have done with 100 numbers here for some value of lambda, and you can see the blue line is the empirical probability distribution function generated from the samples, and red is the theoretical or the target probability distribution function. And with 10,000 samples the match is a lot better as to be expected, and again we can perform the Kolmogorov-Smirnov test and be sure that we have succeeded in simulating acceptable random numbers. So, this is a map of xi plus 1 versus xi. Again I do not see any discernible order in this, so it looks fine. Another example, how do you simulate Rayleigh random variables? So, Px of x in this case is x by sigma square exponential minus x square by 2 sigma square, where x runs from 0 to infinity, and the distribution function here becomes you can integrate this and we get 1 minus exponential minus x square by 2 sigma square. So, the transformation we are looking for is 1 minus exponential minus x square by 2 sigma square is equal to phi of z. So, you invert this and I get x, which is a messy function of z as shown here. So, once this is determined, the ball gets rolling, we simulate random numbers z normal 0 1, apply this transformation, get sample of x. So, here with 10,000 samples for sigma equal to 2, I see that the match between simulation, which is blue line, and the red, which is the target, is quite good. Now, similarly we can I have done a few more exercises. I have generated 1000 Weibull random numbers on and displayed on Weibull probability paper. It looks fine. Now, what happens if we are not in a position to invert the probability distribution function? How will you proceed? For example, in our earlier studies on envelopes, I got the probability distribution for an envelope as displayed here. There is a Bessel's function here, and R sits here, and R sits here, and R is here, and how do you, this is density function. So, you have to integrate this with respect to R and find the distribution function and then invert it. So, it is very unlikely that you will succeed in this. Similarly, you take the probability distribution of the phase, you have cos square phi, sin square phi, sin phi, cos phi, etc., etc., and it is very unlikely that you will be able to first of all find out the probability distribution function and then invert it. So, how do we proceed in such situations? So, the method of transformation of random variables does not seem to I mean it is not a promising method for these problems. So, there is a method known as accept and reject methods, accept reject methods. So, the logic of this is as follows: let x be a random variable with PDF Px of x. Let it be required to simulate samples of x. Now, what I do is I define a random variable u such that it is distributed uniformly in 0 to Px of x. Okay. Now, that would mean u and x are mutually dependent with the joint density function u of u comma x is equal to 1 whenever u lies between 0 and Px of x, where x itself takes values from minus infinity to plus infinity, otherwise it is 0. How do we get the marginal density function of x from this? You have to integrate with respect to u. Now, that is nothing but u is 1 for whenever it takes value from 0 to Px of x, therefore, it is integral 0 to Px of x du. So, Px of x equal to 0 to x Px of x du, I mean it is a very profound result, quite simple to understand, but it has very deep implications. So, let us look at this again. Px of x is 0 to Px of x du. Thus, Px of x is obtained as a marginal probability density function of Pux u comma x. Now, can we simulate samples of x and u without inverting Px of x by using this logic? Now, this u is known as an auxiliary variable. So, the story here is we generate x comma u by generating uniform random variables on the constraint set, that is set of x comma u, such that u takes value between 0 to px of x. That means simulating x from px of x, that is according to this probabilistic law, is equivalent to simulating this pair x comma u, so that this set constraint set x comma u is uniformly distributed. Okay, this script u means it is uniformly distributed. Now, how do we translate this idea into a working algorithm? Now, I will not get into too many details, I will illustrate this by a few examples and a simple explanation. So, let x be a random variable with PDF px of x and x belong to I, an interval I. Now, what we do is we represent px of x as a number m into g of x into h of x, where m is a number greater than 1 and g of x takes values between 0 and 1 and h of x is a valid probability density function. Now, let u be between 0 and 1 and y be the random variable with PD of h of y, and h of y should be such that you should be able to sample y from h of y. Okay. Now, py of x conditioned on u less than or equal to g of y can be shown to be px of x. How do you show that? You use Bayes' theorem and consider py of x conditioned on u less than or equal to g of y. Using Bayes' theorem, I can write it like this. That means, use conditional probability and then rewrite this in a slightly different form. Now, we consider now here there is one probability u of u less than or equal to g of y condition y equal to x. Let us consider that here, and this is nothing but g of x, because u is uniformly distributed. So, this is g of x. Similarly, u less than or equal to g of y is if you carry out this analysis, you can show that this is equal to 1 by m. Now, therefore, if you substitute this and this into this, we can show that this conditional probability density function is nothing but px of x. So, the algorithm is, so you generate x from g of x and u from 0 to 1, and we accept y equal to x if u is less than or equal to px of x divided by m g of x, or you go back and do this calculation again. Now, I will give an example. Let us consider a probability density function which is a triangle between 0 and -1 to +1. That means, I am looking at this blue line. I want to draw random numbers or generate random numbers whose probability density function matches with this. So, what I do is I construct this red line which envelopes this density function, okay, and that will be my m mgx. Now, I will follow this algorithm, and if I do this exercise, I get these numbers. This is characterless, I mean nothing can be inferred from this except that they are lying between -1 and +1, but if I draw the probability distribution function, blue is the simulation, red is the target, and this again is not quite revealing, but if you draw the histogram, you can see that the numbers are along this triangle. Another example, if you want to draw random numbers from a PDF which is made up of say two, this is A1 normal PDF x with mean 2 and standard deviation 1 plus A2 normal x again mean 6 and 1. This is my Px of x, where A1 plus A2 is 1. You can easily see that inverting this for finding x is quite difficult. You can find out Px of x in terms of the normal probability distribution function, but that itself is not very easy to invert. So, how do we proceed? So, we can use this method. So, what we do is this blue line is the probability density function which is the target, and I select this m into g of x to be a normal like density function, and that m is selected so that this envelopes the target density function. That is very important because the theory works only under that situation. So, this graph shows the samples again which are not very revealing, but the probability distribution function you can see that the agreement between blue line simulation, red line there is a target is quite good here. And this is the histogram. You can easily see that there are two modes and numbers are clustering around one point here and another point here. This is 1 and this is 6. So, this is 1 and this is 6. So, if we plot x of I versus I, you can see that the numbers are clustering around 1 and 6. So, these clusters correspond to the modes that we are seeing here. Okay. So, without inverting the probability density function or the probability distribution function, we are able to simulate random numbers. So, this method is applicable when the form of the probability distribution function becomes too complex and we face difficulties in inverting. Okay. I have talked about scalar random variables. How about vector random variables? So, we will start with simulation of vector Gaussian random variables. Suppose I have a sequence of n random variables xi which are correlated Gaussian random variables, and how to simulate. If they are uncorrelated, I have case of n scalar random variables, each one I can simulate separately, and since they are independent it does not really matter. But now they are correlated. So, mean of xi is mu I and the covariance is xi minus mu I, xj minus mu j, Cij. Now, what I do is I first remove the mean and make the standard deviation as 1 by using this transformation. Xi prime is xi minus mu I divided by sigma I. Obviously, the mean of xi prime is 0, and if you write the covariance of this xi prime, you can see that this would be nothing but the correlation coefficient matrix of xi, and along the diagonal we get 1 and this is symmetric matrix. Now, our objective is to therefore simulate xi prime whose mean is 0 and correlation covariance matrix is this fully populated square matrix, symmetric, etc. Now, the strategy we follow is we use a transformation. We propose a transformation y is t transpose x prime. Now, mean is preserved through this transformation, but covariance gets distorted. So, the covariance expectation of y transpose would be t transpose c prime t. Now, t is yet to be selected and I can always select t so that t transpose c prime t is a identity matrix. So, how do we get the t matrix? We study the eigenvalues of c prime matrix. So, we consider the eigenvalue problem c prime alpha equal to lambda alpha, and we solve for the n eigenvalues by solving this characteristic equation, and corresponding to each one of that we get a eigenvector, and since c is positive definite, lambda I will be positive, and these eigenvectors are assembled into a single matrix which is square matrix, and we have seen in discussion on vibration problems that these eigenvectors have orthogonality property, and we can show that phi transpose phi I equal to 0 for I not equal to j, and phi I transpose c prime phi j equal to 0 for I not equal to j. So, that phi transpose c prime phi is I is the identity matrix. So, that would mean you can take t to be phi. So, once I do that, I am able to transform the given random variable. So, there are two step transformation. The first one is simple, I remove the mean and divide by standard deviation. So, xi prime has 0 mean and unit standard deviation and it becomes non-dimensional. So, this is good for us, and then I diagonalize the correlation coefficient matrix or the covariance matrix. So, I have found out t by finding the eigenvector matrix, and moment I find that, what I will do is I will simulate x prime simulate y which has 0 mean and mutually independent elements. I simulate y, use this transformation, get x prime, and from x prime I work backwards and get xi. So, the main task here is to diagonalize the covariance matrix, and the building block is our ability to simulate normal random numbers with 0 mean and unit standard deviation for a scalar case. So, we can do this. For example, if we have a target mean vector of 0.1 and 2.0 and covariance 1.2, 0.3, 0.3, 4.5, I will remove the mean and divide by the standard deviation. I get the covariance matrix is as 1, 1, 0.1291, 0.1291. This is the eigenvector matrix, these are the eigenvalues, and then I have done the simulation in the uncorrelated normal space, use this transformation, work backwards and got x, and with 1000 samples I am able to get a mean vector of 0.1224 as against 0.1 and 2.0311 as against 2.0, and covariance of 1.1077 as against 1.2, 0.2826 as against 0.3, and 4.47 against 4.5. Now again we can do hypothesis test and verify whether we can accept the hypothesis that for instance the marginals are Gaussian, the covariance matrix comes from a population whose covariance matrix is this, etc. So for that of course you need to know the sampling distribution of covariance, estimates of covariance, that we have not discussed. Maybe at some point in future lectures I may be able to say a few things on that. So this is PDF of x1, blue is empirical, red is analytical target. This is for x2. So in either cases the comparison between theory and simulation is quite good, and these are this is a display of Z2 versus Z1. Again we do not see any discernible patterns. Okay. So a vector of Gaussian random variables does not pose any major difficulty for us. How about vector of non-Gaussian random variables? So there are different approaches. One is what is known as Rosenblatt transformation. So I will illustrate this. This is an extension of a method of transformation of PDFs. So let x1 and x2 be two Gaussian random variables, and a joint probability distribution function p12 and density function lowercase p12 and marginal PDFs p1 p2, marginal densities p1 p2. Okay, fine, that describes x1 x2. Now let u1 be distributed normally in 0 with mean 0 and standard deviation 1, and similarly u2 normal with mean 0 and 1, and let u1 and u2 be independent. So I begin by defining p1 x1 equal to phi u1 and p2 of x2 condition on x1 as phi u2. Based on this transformation we can show that x1 and x2 are the density function of x1 and x2 will be according to the target joint density function. So to do that we apply the rules of transformation of random variables and find the Jacobian, and we can do this calculation. The details are displayed here, and we get in fact the joint density between x1 and x2 will indeed be the target density function. So how do you implement the method? You simulate u1 and u2 and you find out x1 by x1 equal to p1 inverse of phi of u1. Then you find out x1 is already simulated for every value of x1. You come here and find out the inverse of this. Okay. So you will be able to proceed with the implementation. Now this is generalization to n random variables is straightforward, but it would involve inversion of increasingly more complicated conditional probability distribution functions. If you can do it, you will be able to proceed according to this. Now most often we will not be in a position to provide the nth order joint probability distribution function of random variables in practical applications. What we would be able to provide would be the first order probability distribution function and a covariance matrix. For example, if you see the Joint Committee on Structural Safety, there is a document which has attempted to provide certain canonical distributions for properties of construction material, and if you look at the properties of steel, according to this document, the 5 variables of steel as a material, namely yield strength, ultimate tensile strength, Young's modulus, Poisson's ratio and ultimate strain, the coefficient of variation is specified. Mean can be taken from your test coupons or whatever, but the coefficient of variation is this, and a correlation coefficient matrix is given here, and also stipulated is the fact that the first order probability density function for each one of these variables is log normal. Now I want to simulate samples of these 5 random quantities which have this first order PDF, this coefficient of variation and this correlation coefficient matrix. Obviously as a set of 5 random variables, the information that is provided here would not lead to a complete specification of 5 dimensional random variables. For that you need a 5 dimensional probability density function, but most often, as I was telling, in practical application the kind of information we will have will be of this kind. So how do we proceed? So, we start with the case of 2 random variables, let x1 and x2 be 2 random variables such that x1 and x2 are not completely specified. Knowledge of x1 and x2 is limited to first order PDFs and the covariance matrix. So, now how do we simulate x1 and x2? So, the question is, if you transform x1 and x2 to a standard normal space, you can start with standard normal random variables and transform back to the required x1 x2 random variables. So, here what we do is we define Px1 of x1 as phi of u1, Px2 of x2 as phi of u2, where u1 and u2 are IID normal, mean 0, standard deviation 1, not IID, sorry, they have correlation coefficient rho 1 2 star, they are not IIDs, they have 0 mean and unit standard deviation, but they are correlated. This correlation is unknown. What I know is the correlation between x1 and x2. So, I need to develop a method to find correlation between u1 and u2. So that the correlation between x1 and x2 will meet the specified target value. So, again we go through the rules of transformation of random variables, and we can indeed show that as far as probability density functions on marginals are concerned, this transformation leads to satisfactory results, there is no problem there. But the question of finding rho 1 2 star, that means we will be, once I implement this transformation, u1 and u2 will have this correlation coefficient. So, to simulate u1 u2 I need to know this. So, how do we proceed? So, what we do is we write an expression for rho 1 2 star using this transformation. So, if I do that, I get, it is fairly involved, but one could easily digest this, it is tedious but not very complicated. So, if you do this, you will get an equation for rho 1 2 which is given, the correlation coefficient between x1 and x2, and rho 1 2 star which is the correlation coefficient between u1 and u2 which is not known. So, all other parameters in this equation are known and we need to solve for rho 1 2 star. So, this is an integral equation and it looks like quite formidable to solve, but there is a very simple strategy to deal with this. So, what we could do is, we know what we are asked to do is, for a given value of rho 1 2 which is on the left hand side, we need to find rho 1 2 star which is buried inside the integrand. But we know that rho 1 2 and rho 1 2 star are both bounded between -1 and +1. So, what I will do is, I will start by assigning values for rho 1 2 star between -1 and +1 and evaluate this integral and find out what is rho 1 2. After I do this exercise for a few complete range of -1 to +1, it would, if there is a root, it will certainly lead to the one that we want for rho 1 2. So, the game is, what we do is, we run the calculation and find for every value of rho 1 2 star, we find out rho 1 2 and this is a target value. So, once I do this, I will have the value known in the neighborhood and I can use either a better approximation or an interpolation and arrive at the corresponding rho 1 2 star which is precise. We will have a table of values for rho 1 2 in terms of rho 1 2 star and we can interpolate or do some refined calculations and arrive at this. So, this works quite well in application. Now, this I have illustrated for 2 dimensional case, you can generalize to n dimensional case. So, you have to take pairwise, this transformation by the way is known as Nataf's transformation. So, this can be extended to n dimensional case, it requires a solution of an integral equation, this itself can be done numerically, and for n dimensional case the number of integral equations to be solved becomes n into n minus 1 by 2, and other forms actually within the framework of this, suppose we consider 3 random variables. It may so happen that for a pair of 2 random variables I know the joint density function. So, what I know, for example, could be marginal density of x1 x2 x3, joint density between x1 and x3 and covariance matrix between x1 x2 x3. So, we are falling short of complete specification by different way, we can fall short of the complete specification in many ways, but in each one of the cases the Nataf's model can be used and whatever is not available can be, I mean we can simulate, we can transform with the available information the 3 random variables or n random variables to equivalent normal random variables and implement the method. So, steps for simulation of 2-dimensional Natta random variables, you solve for rho 1 2 star by solving this, then simulate z as 0 comma rho star, then simulate x1 and x2 using this transformation. So, to simulate z as 0 comma rho star, again you have to find eigenvalue analysis of rho star, generate independent normal random variables, apply the transformation and then simulate z. And once you simulate z, you have to get into this nonlinear transformation and you will be able to get x1 and x2. Okay. Now, obviously this cannot be done with pen and paper, you need to write a computer program for this, then only you will be able to see the working of different steps of this method. So, let me consider a couple of examples. So, first example is x is uniformly distributed between 0 to 100 and y is exponentially distributed with a parameter 1 divided by 0.08 and z is Rayleigh distributed with parameter 12 and the correlation coefficient matrix is displayed here. Now, I want samples of x, y, z. So, when I simulate, I should get uniform distribution for x, exponential distribution for y and Rayleigh distribution for z, and the correlation coefficient matrix for these 3 random variables should be similar to this. So, we have done this I think with 5000 samples. Now, the target mean for this is 50, 12.5 and 15.0398, that can be calculated from the given values of the system parameter. With a simulation, we got a mean of 50.25, 12.22, 15.29. And standard deviation target is 28.86, 12.5, 7.8 etc. and simulated one is 29 point something, 12.29, 8.0 etc. Again we can test the hypothesis whether the samples are drawn from a population with mean 50 or not. You can do a hypothesis test on variance, you can use chi-square test, here you can use Gaussian sampling distribution, here you can use chi-square distribution, so on and so forth. How about the simulated covariance? What was simulated, this is a target and what was simulated is displayed here. There is a broad agreement, there is no reason to suspect that things are wrong. Now, some displays of these results. The 3 target probability density functions are shown here. This is blue is a uniform, this is a exponential, this is Rayleigh. The simulated PDFs. So, the red and the blue is the simulation result for uniform, the red and blue match well, here pink and cyan and green and black. This is Rayleigh, this is uniform distributed, this is exponential. So, again you can see that the empirical probability distribution function and the target probability distribution function are in good mutual agreement. The plot between rho star and rho is shown here. So, this is -1 to +1 and this is -1 to +1 and this is for 1 2, that is x1 x2, x1 x3 and x2 x3. So, you can, this is a plot that we get by solving those integral equations for various values of -1 to +1 for rho star, and this is rho that we get and we know the target number here and we can read off from here the corresponding rho star. So, this plot has to be generated as a part of the solution to the problem. So, this simulation method works for, therefore, this is a reasonably complicated problem in simulations and this method works quite well. One more example, this is some displays of samples, this is samples of uniformly distributed numbers, this is exponentially distributed numbers, this is Rayleigh distributed numbers. I have one more example, x1, x2, x3, x1 is log normal, x2 is log normal, x3 is type 1 asymptotic and the target mean 40, 50,000, standard deviation 5, 2.5, 200 and the correlation coefficient matrix is this. So, we can run through this calculations again. So, this is the equivalent correlation coefficient matrix for the Gaussian random numbers, this is the rho star. Now, we do checks, the mean that we got is 40.02, 50.02 with 5000 samples and 997, and then this thing should be compared with 40, 50 and 1000. So, this is 40 point something, 50 point something, 997 point something. Similarly, standard deviation 4.95, 2.49, 198, so on and so on. And this is simulated correlation coefficient matrix. So, again things seem to be all right, and these are the 3 target probability density functions x1, x2, x3. To depict how non-normal they are, I have also shown on this graph the corresponding plot of a normal random variable. So, the difference between the two gives us an idea on the non-Gaussianity of the corresponding random variable. This is simulation results on x1, x2 and x3. Again blue is simulation, red is the target, and we can see that there is quite a good mutual agreement. Now, a slightly more complicated example. There are 7 random variables, x1 is uniform, x2 is log normal, x3 is log normal, x4 is normal, x5 is extreme value probability density function of type 1, x6 is again extreme value type 1, x7 is normal, and p1 and p2 are the parameters of these distributions. There are 7 random variables, and this is the mean and standard deviation of the 7 random variables, and this is the target correlation coefficient matrix. So, it is not diagonal, there are off diagonal terms here you can see, and some of them are negative, some of them are positive, and along the diagonal we have unity. Now, we need to simulate say 10,000 numbers or 5,000 numbers of these vectors of realizations of x. With 5,000 samples and using the Nathop's transformation method, the problem is solved, and we have the simulated value of the mean, the standard deviation and the correlation coefficient matrix, and these have to be compared with the corresponding target values, and again they are quite good in good agreement between the target and simulated numbers can be evinced in these numbers. That agreement, again let me emphasize, can be actually be objectively assessed using hypothesis testing methods with using the appropriate sampling distributions and for specified significance levels. Now, this is the equivalent row for the Gaussian random variables obtained by solving the 10 into n minus 1 by 2 number of integral equations that is displayed here. On this, of course, there is no verification, this is an intermediate step. So, these are the random variables that we are simulating. The red plots are the target probability density function, black is the standard normal, just to it is not the standard normal, the corresponding normal distribution with the same mean and same standard deviation, just to give an idea on how much these specified first order distributions depart from the normal distribution. So, there is considerable departure here, here, and of course, uniform distributed there is a this x1 there is a good departure, and whereas here although the random variable is log normal, the agreement is between normal and non-normal, the differences are not that much. So, these simulation results with 5,000 samples, blue is simulation, red is the target, this is uniform distribution, this is log normal, I think this is normal, and so on, extreme values and normal, so on and so forth. So, again the agreement is quite satisfactory. So, this method seems to work quite well. These are realizations, these are characterless just for to get a visual feel for what we are doing. These are the numbers, and we have reached the end of this lecture. So, to summarize, so far what we have been able to do is to develop methods to simulate samples of scalar Gaussian, non-Gaussian random variables and vector Gaussian and vector non-Gaussian random variables. For vector non-Gaussian random variables, we have two methods, that is the Rosenblatt's transformation method and the Nathop's transformation method. Rosenblatt method can be used if you have complete specification of the vector non-Gaussian random variables in terms of their joint density functions. The NATAF can be used in case when information is partial. So, in the next lecture what we will do is we will extend this discussion to cover cases of simulation of random processes, how to simulate samples of random processes where a probabilistic description of the underlying random process is provided. This process can be Gaussian or non-Gaussian, scalar or vector, completely specified or partially specified, and let us see how to go about doing that in the next lecture. So, at this point we will conclude this lecture.